Hello everyone, welcome to Big Data Thoughts. Wish you all a very happy new year. And we have been talking on different topics in the last year, but for some time I was not able to post some videos. But then this year I again plan to resume back to the weekly schedule where I'll be posting every Monday. So today's topic is evolution of data architectures. We have been living in the world of data, and there is huge data. We are talking about big data and distributed architectures. So it is very important to understand how all of this evolved, from where we started, what was the need to evolve, and where we are. So the whole progression of data architectures. So let's get started. First of all, let's look at the timeline starting from the 80s till 2020s, because thereon pretty much it is still evolving, but the concepts have been around data lakes and lake houses. So we look at the timeline from 80s till 20s. So first of all, in the 1980s, initially we had relational databases, and they were very prominent. We had data which was structured, that could fit into tables, columns, which could be established in terms of primary foreign keys. The relationships could be established. But then, as and when the data started growing, now relational database had its own advantages in terms of having integrity that you can maintain. You can enforce a particular schema on the data, and that way you can actually define how your data should exactly look like. It had ACID properties, consistency, atomicity, and all of that, right? But as and when the data started growing, there was a need to have a system which would be actually based on these concepts of ACID, etc., but which would be able to evolve with the growing needs of data. So that's when in the 1990s we saw data warehouses coming up. It had a capability to store high quality data. There were standard modeling techniques that were developed by Kimball. Ralph Kimball is known as the father of data warehousing, and he has given concepts like star schema, snowflake schema, which tells you how you should model your data to serve your analytical purposes. Now, data warehouses had all of those benefits that an initial RDBMS had, which was your ACID transactions, and they were very good fit for business intelligence and analytics. So those were very prominent, but it had its own issues, like the formats were closed. There was support for only SQL because it was built on the basis of a SQL fundamental. It did not have any support for machine learning, for streaming. Scaling was also difficult. So in the 90s, though it solved all the purpose, and even today we are using data warehouses a lot, but then as and when the data started growing even more and the formats of data moved from being only structured to semi-structured, unstructured, data warehouses were falling short. Then somewhere around the 2010, the concept of data lake came in, which was nothing but a storage or a data store which can allow you to store data in from variety of sources in variety of formats. It was not, data lake as a concept was supposed to give you the flexibility of not thinking about the schema beforehand. So when we had RDBMSs, data warehouses, we were always thinking about the schema first. So it was schema on write, which meant before writing the data, you knew that this is the schema the data needs to adhere to. But data lakes gave us the flexibility to think about schema later while we are trying to read the data. While writing, you could write any kind of data, structured, semi-structured, unstructured, any type. It would allow you to do that. It was very scalable because this whole data lake is based on the distributed architecture. So you can horizontally scale. When you scale vertically, there is definitely a limitation. You can scale up to only a certain point. But when it is a horizontal scaling, it is very easy to scale up. So data lakes provided that entire flexibility, and they opened up a new world where we could realize different use cases. It supported machine learning and AI. It allowed storage of any kind of data without thinking about the schema beforehand. The schema was while you are reading the data. It could support open formats, and it was very scalable. So it kind of met all the demands of growing data. But then when people started using data lake, they started missing that whole thing about acid properties, about reliability that the acid properties gave, and they wanted to have best of the both worlds, the SQL world and the data lake world. That's when a combination of both of these concepts came in, which is very prevalent these days. Data lake houses. What does it mean? It is a combination of data lake plus data warehouses, benefits of both the world. That's why they are known as data lake houses. They support both BI and MLAI workloads. There is a standard storage format. It supports ACID properties. In addition to that, it still has scalability. So it is like best of data lake and warehouses put together, known as data lake house. So that's the overall journey of almost like from 1980s till 2020s, how this whole evolution of the architectures happened because of the growing need of different use cases and the growing volume of data. Okay, now whatever we spoke, as briefly I gave, right, we'll speak in detail about each of these. So as I said, the relational databases, what was the standard? The standard was SQL. It was a SQL language was used, and there were people who started learning SQL, and then SQL was very easy, intuitive to use. It was not like a program that somebody had to write or learn, so learning curve was lesser. It was the standard storage technology for any enterprise application, and that went on till the 1990s, almost for a decade. And the major reason of this whole popularity of the relational databases was this whole concept of transaction. So you could define that these are the set of instructions that I will logically call as a transaction. Either all of these go through or they fail, because there are certain use cases where you don't want, let's say you have 10 steps to perform, you don't want that 5 of them go through, there is a failure and your database goes into inconsistent state. What you wanted, or what people wanted, was to have all of these 10 steps to be performed either together as a success or it should be rolled back. So that was the whole concept of transaction, and this is something which was a USP of a relational database. Another thing that a database transaction, now when we talk about a transaction, what that transaction is supporting, basically ACID properties, and this was very important in terms of reliability and consistency. Whatever I am committing to a database is not an intermediate commit, it everything goes through and then a commit happens. So it had atomicity, consistency, isolation and durability. These two things, the concept of transaction and ACID properties, and maybe one more, simplicity of writing SQL, that made this whole relational database a very powerful concept, and it was there getting used prevalently by every enterprise for that entire decade. After this came the data warehouses. Like I said, it was an evolution from RDBMSs to this world of data warehouse. Now, the difference here is it's a central repository. It's a relational repository which has all your historical data as well as the current data. So it is capable of giving you this whole view of historical plus current data. It's a unified view to the business. And you don't have to go to different systems to get data. It's a central store which is getting data from multiple systems, and then it gives you a comprehensive view across all of those systems. So it became very popular as a business intelligence or analytics tool. And the whole concept of ETL that we have been hearing, extract, transform and load, was there in data warehouses, where you are extracting data from multiple sources, transforming it and then loading it. So typically how a data warehouse would look like, you would have a layer of data sources, you would have a staging layer. Now this staging area is meant to do all the transformations and then load it into the data warehouse. And data warehouse will have multiple layers: raw data, metadata, aggregated data, and on top of that you can have OLAP cubes, you can have reporting, data mining being done. So it will solve multiple business intelligence use cases. So that's how we evolved from RDBMS to data warehouses. So data warehouse, just imagine as being a central repository which can house a humongous amount of data, including historical and current, and it gives you a comprehensive view of the entire enterprise. Then came in the data lakes. Now there is a difference between the data warehouses, how they operated, and the way data lakes operate. Because data lake is also a central repository, like we saw in case of data warehouse, but the major difference being the kind of data that you can store. Data warehouses were still relational, storing only data which can fit into rows, columns, and tables, which is primarily structured data. But as and when data grew, different kinds of use cases came in. It was very important to have a storage where you could store any kind of data, any format of data. That's where data lakes came in. That need gave rise to data lakes, where it is still a central repository with any kind of data you can store, and it can scale because it is a distributed setup, and we can scale horizontally by adding multiple nodes. At a high level, how will it look like? And is you will have multiple sources, and this is actually extract, load, and then transform. It is no longer ETL, it is ELT. Another major thing, as I said, schema on write was RDBMS and data warehouse, where while writing itself you had to enforce a schema and fit the data into the schema. So you could practically lose a lot of data which is not fitting into that schema. But in a data lake, it is schema on read. So there is no enforcement while writing. You can write anything. While reading, you enforce a schema. So you're not losing any data. And typically, you can categorize it as a raw layer, as silver. So this bronze, silver, gold is nothing but as and when you keep on cleansing, massaging, transforming the data, it becomes silver or gold. So bronze is your raw layer. Silver is like your filtered, cleansed, augmented data. And gold is like your aggregated data that the business would use. So this raw layer is just as is data. As you got it, you stored it. You're not losing anything. You can go back later in time and then look at what you stored. This is more definitive with a structure, with enforced schema. The schema can evolve, of course, but you still enforce something. Here you don't enforce anything. You enforce, and this is where you are continuously updating the clean data so that downstreams can consume it. That's how we moved from data warehouses to data lakes. Okay. Why data lakes? I did speak about one of the USPs is that you can store any kind of data. That's a big advantage of data lake. Structured, like what we were doing in RDBMS or data warehouses. Semi-structured, like CSV, XML, JSON. And these days JSON etc. is very common. Unstructured can be email, some text, logs, etc. And the other advantage is the flexibility that a data lake provides in terms of storing, in terms of processing different data formats, and it becomes a one-stop shop for any kind of data. So you can store data from any place. Usually you incrementally build the data lake. You don't bring in everything at one point. You identify use cases, prioritize them accordingly, keep on building the data lake by bringing in data from multiple sources. Okay. Now, another advantage. Typically, lakehouse or data lake, both of them will have these advantages, and it is important to understand why these are more flexible or better than our earlier data warehouses. Okay, the other critical thing to think about is segregation of storage and compute. We often overlook this point, but this is very important and critical to the success of data lakes. Why? Because you are no longer tightly coupling the storage and the compute. You don't have one machine where you are trying to scale vertically, or you're tying up the storage and compute. So if you have to scale, you have to increase both storage and compute. It's not like that. Now storage has always been cheaper and compute has been expensive. So we definitely want to decouple it, which means only when I need to increase storage will I increase storage. And most of the time the data is huge. We may want to increase the storage, but not necessarily the compute. So we can scale them independently. A simple example, right? If we built a data lake where it's a distributed setup, you have created a cluster, you have machines which are heavy on storage, you're able to store. Now you want to increase that storage, and typically on cloud, what we do, if we are using Amazon, we are using S3. If we are using Azure, we are using the ADLS. I don't necessarily have to think that if I have to increase the storage, I have to go and increase the compute also. So, with the advent of clouds and the flexibility that they provide, it is very easy to scale compute and storage independently, and it is one of the biggest selling points for a data lake. Then, of course, horizontal scaling. Because it is distributed computing, you can have less powerful machines, but you can scale them horizontally by adding nodes. And that is the benefit of data lakes, that it allows you to scale as per your need. So you can grow and shrink as per your need, and that has become possible with the advancement in cloud architectures. So with cloud architectures and distributed computing, this whole scaling has become very easy and on demand. It saves you a lot of cost because you're operating on cloud. You don't have to worry about projecting the demand and then buying machines, putting them in a cluster. You can simply grow as per demand and shrink as per demand. So that is another advantage. Schema on read, of course, I spoke about it. Schema on read is also one of the biggest USPs because you are not enforcing any schema while writing. You can store any kind of data in the raw data layer. Later on, based on use cases, you can have different ways in which you are reading it and enforce a schema. So, schema enforcement is only during the consumption. That gives a lot of flexibility in terms of what we can store and process. Last but not the least, data lake houses. So we looked at RDBMS, data warehouses, data lakes. Why data lakes? The advantages of this whole distributed setup. More or less the advantages are similar what we have for data lake house also. But this one is even more evolved concept because we are merging the benefits of both data warehouse, which is the reliability, the asset properties, the structure, along with the lake house benefits. So it gives you low cost, scaling flexibility, asset properties, and it is addressing both all the limitations that a data warehouse had or a lake house had. It is a combination of both. And how typically would it look like? So existing, you can have data lake built on Amazon S3, Azure Data Lake Storage, Google Cloud, IBM Cloud, any of them. You can have existing data lake. On top, you can have a delta lake. Now we have spoken about both these concepts in separate videos of data lake and delta lake, but this is to just give an overview of a data warehouse plus data lake combination, a lake house. How does it look like? You will have the data residing, and on top you will have high performance query engines, like it can be Spark, Flink, whatever. It can be any of the existing technologies. So what it is doing, it is bringing in cloud-based data storage is there. You have scalable low-cost data stored on cloud. On top of that, you have a curated layer of data. And on top, you have high-performance query engines, which are getting utilized by any of the platforms for their use cases, whether it is machine learning, data science, BI, or streaming analytics. So that's how a lake house is a much more advanced version of a data lake. And one point that I would like to also speak about, you may hear this when you hear about data lake houses, is the Medallion architecture. Now, this is a concept which was introduced by Databricks when the data lake house came in. It's an architectural pattern which talks about your bronze, silver, and gold. We saw this in the data lake house also. And this concept came in where we are segregating data based on how we have transformed or cleansed it into different layers, and this is known as a medallion architecture. You have data from multiple sources, you take the data, put it in a as is, and call it a bronze layer. It's just a logical name. Then you cleanse it, call it silver. Then you aggregate it, you call it gold. Gold is nothing but a ready-made data for business intelligence tools or users to consume it. But just to keep a note, if this term comes up, what does medallion architecture mean? So that's what it is. Okay. The layers, as I spoke about, bronze layer is nothing but a layer where data is ingested from the sources, and it is a as is layer. You can augment that using some metadata and associate metadata with it, like when did you load that data, which source, etc., to enrich that whole raw layer. But essentially bronze layer is a as is or raw data layer. Silver layer is data from the bronze that you have picked up, and then you have cleansed, normalized, merged, and confirmed that data. This is the enterprise view of data across different subject areas. And then finally you have a gold layer, which is a consumption ready aggregated layer. It can be star schema, snowflake schema, however you want, but it is essentially a data which is aggregated and like pre-aggregated and kept for the consumption point of view. Now this was a complete quick snapshot of how data architectures evolved, their advantages, and why each of them came into existence. I hope this has given you some perspective about the evolution, and please like, share and subscribe for other interesting videos. Thanks everyone.